Hi there, welcome to your second video on volume. Let's begin by recapping what we saw in the last video before jumping ahead to the next topics in geometric volumes. So what we began with last time is defining geometric solids, and we kind of looked at polyhedrons, solids, and non-polyhedron solids. So let's take a look. Okay, so in the top row, which one do you believe does not belong in that group of prisms? I hope you chose E. They all look like the same idea. Bottom shape, top shape, and a 3D solid that grows from the base to the other base, right? We talked about that idea. There's these bases, they're parallel, they're congruent to each other, and you have a prism like that. However, a polyhedron also needs to have all faces that are polygons. And we said a cylinder does not have polygonal faces. Therefore, even though it behaves like these other shapes, where you begin with a base and you grow up to another congruent base, it is not a polyhedron. It is a prism, or a curved solid. Sorry, it's not a prism. It's not a polyhedron. Let's move on to the last ones here. How about from these bottom ones? Which one doesn't belong here? And in this case, I hope you chose B for the same reason as above. B is a curved solid. It is not a polyhedron. It doesn't belong with the other polyhedrons. All other polyhedrons have polygonal faces, whereas the cone does not. It has a circular base and then this curved surface. And the cylinder also does not have polygonal faces. So they stand out. They are still 3D solids, but they are not polyhedrons. Okay, let's recap some more. We classified then polyhedrons and curved solids. Polyhedrons were shapes like these that we just saw. Some are called prisms, where they have two bases, and some are called pyramids, where they have a single base. And then we had curved solids, which are also 3D shapes, but they are not polyhedrons, and they are these three here, typically. Okay, we said a prism is a polyhedron with two congruent parallel polygon bases. For example here, these are congruent and parallel, these are congruent and parallel, and so on, so on. Those are prisms. It looks like the whole shape grows from the base, and everything is a polygon. Okay, bases name the shapes. So triangular, rectangular prism, square prism, pentagonal prism, hexagonal prism. Let's keep going. When you connect the bases of a prism, these are called the heights. It goes from base to base. So even if this hexagonal prism fell over on its side, these two things would still be called its bases, and this line would still be the height. Even though the shape is laying on its side, this would still be called the height, okay? Now, we moved on from there to volume, and we talked about volume as being the amount of space inside a shape, shown well with this liquid here, filling this shape. And we said there's perimeter, area is two-dimensional, volume a three-dimensional measure. We defined volume as the amount of space in a solid, or better yet, the number of cubic units a solid contains. We said you can fill any 3D shape with little cubes. Like if this one here was measured in meters, we could say how many meter by meter by meter cubes would fill each of these. So that is the volume, how many cubic units fill the shape. And finally, we said volume, you can think of it as the base area of a shape times its height. And the reason is we take the base and we stack it up until we get the full volume. All right, so we're stacking bases. So base area times height. And likewise, in this is also a prism. The base area is a triangle. We can stack all those triangular bases. So base area times height would be our volume. And finally, cylinder behaves the same way. We have all these circles stacking up. Those are the bases. So base area times height. In this case, a circle has an area of pi r squared. So our volume is pi r squared times height. Okay, now we're back to a new place. We've recapped what we saw before, and now we're going to move into three main solid shapes. One is called a pyramid, one is a cone, one is a sphere. Let's take a look at each one by one. So let's begin with pyramids. A pyramid is a polyhedron with one polygon base and triangular faces. So all the other lateral faces are triangular and they meet at a common vertex. This is a rectangular prism, pentagonal prism, and a triangular, sorry, did I say prism? Pyramid, pyramid, and triangular pyramid as well. We are naming them by their base. Okay, the heights in these are a little different than in prisms. The height has to be perpendicular or make a 90-degree angle with the base, so the height lines go straight from the vertex down to the base like that. All right, what is the volume of a pyramid? So like we said already, a prism, you can just stack bases to get the volume, right? But in a pyramid, if you took that base there and you stacked it up, would that be a way to represent the volume? Well, no, because as you stack it up, the base does not remain the same size, right? The layers would get smaller and smaller as you get towards the top here. So the question then is a new question. We cannot stack bases to find the volume of a pyramid, but we can consider how many of these pyramids would fit inside this one here. So how many pyramids would fit inside the prism that has the same base and the same height? In other words, think of it this way. If you filled this with water and then you poured it in here, how many of these pyramids would it take to pour in here to fill this entire volume? What do you think? Well, the answer is 3. And amazingly, it's exactly 3. If you have the same height and the same base, it would take exactly 3 of these to fill that one. Amazing. So here is our formula. If our volume of a prism was base area times height, and now it takes 3 of these to fill that, the formula must be 1/3 times the base area times height, because it is 1/3 of the volume of this one. Remember that for pyramids, always 1/3. Okay, 1/3 base area times height. So that is our recap, our volume of a pyramid. Write that down, and let's move on to our next 3D solid. The next 3D solid is a cone, so it's time for cones. Here's a cone. A cone, you know, has a circular base, and like a pyramid, everything goes towards one vertex. But a cone is not a polyhedron. A pyramid is, but a cone is not, because it does not have polygonal faces. This is the height here. In a cone, that diagonal length along the side is called the slant height. Remember that. Of course, we have a radius here as well. Okay, so a cone is defined as a solid with a circular base, and all the segments from a vertex to the circle. There are infinite segments, or imagine lines connecting from that vertex down to that circle, infinitely. All right, that is our cone. It is not a polyhedron, because the faces are not polygons. Now, let's ask the same question we did for a pyramid. We know if we stacked the bases of a cylinder here, if you stacked all these circles, you would end up with the volume of the cylinder. But in a cone, just like with a pyramid, you cannot stack the bases to get the volume, because these base circles will get smaller and smaller. So the question is the same as a pyramid. If we filled this cone with water, how many cones would it take to fill this cylinder that has the same base and the same height? What do you think? The answer, again, just as we had with a pyramid, is exactly 3. That's kind of amazing. It's not coincidental. There's ways to look at this, but 3 cones exactly would fit in a cylinder with the same base and height. Amazing. So therefore, if the volume of a cylinder is base area times height, or area of a circle base times height, then what is the volume of a cone? Well, it must be the same formula, but 1/3 of it. 1/3 base area times height, because it is 1/3 the volume. All right, key formula. Let's make sure we have that noted down as well. And let's move on to our third solid for this video. The third solid is a sphere, so it's time for a sphere now. Okay, so let's introduce spheres. Here is a sphere. It has a radius. And here is what's called a hemisphere, which is half of a sphere. Let's remember that vocabulary as we apply it to different scenarios. So a sphere is the set of all points in space equidistant from a fixed point to the center. So imagine you had this fixed point here, and then you had all these radii going in every direction. Usually when we have a circle, we just think of radii along one circle, but imagine now radii going in all directions. All those radii are the same distance, and if they create all the points on the exterior here, they create a sphere. So that's our center. This is our diameter. This is our radius. And this, the biggest circle within a sphere, is called a great circle. All right, so what is the volume of a sphere? Well, it's given by this formula here, 4/3 pi r cubed. We'll take a look at why that works, one approach to it in class when we meet. But for now, know that that is the formula and write it down. And again, here's the summary of the volumes we've looked at in this video, which is volume of a pyramid, and a cone, which are basically the same in terms of 1/3 times the base area times height, and then the volume of the sphere here. Let's apply these now in a few problems. So problem 1, find the volume of this pyramid. Give it a try. Okay, we need a height, right? To find the volume of something, we always need the height, and this 12 is not the height. That's the slant height. It's the height along the side wall of the pyramid. That's not the height. The height has to go from the base up to the vertex and be perpendicular to the base. So this would be a height. If we're trying to find that height, we can imagine that this hits directly in the center of this side. And if this has a length of 10, then this length here is 5. Okay, now we have a right triangle sitting in there with a length of 5 here, and this is 12. So that will allow us to solve for height using the Pythagorean theorem. So here's Pythagorean theorem. Let's find the height. The height is 10.9 inches in this case. All right, so now to find volume, we always do base area times height, right? But this is also a pyramid, so there's something else to consider. So let's try it. Volume is 1/3. Yeah, don't forget that. A lot of students forget that. We do 1/3 times the base area times height. The base area is like a square, so I just put s squared here to represent side times side. And in that case, it is 1/3 times the base area, which is 10 times 10, 10 squared, times the height, which we just found to be 10.9. So there's everything substituted in, and our volume works out to this value here. Don't forget to put units or inches cubed, because don't forget, a volume actually represents how many cubes can fill this shape. How many little 1 by 1 by 1 inch cubes can fit in here. And of course, it's weird because some cubes will have to be shaved, you know, cut a part of it off so it fits in here perfectly. But in total, there will be this many cubes. It's amazing. Let's try problem 2. Find the volume of this cone. Okay, just as with the last one, we did not have the height, so I drew it in here, perpendicular to the base. Now, again, Pythagorean theorem one more time, we need the height. We can't use 7 as the height, that's our slant height. So find the height using Pythagorean theorem. And the height works out to 6.7 yards in this case. And then we can find the volume, because volume is 1/3 base area times height. And the base here is like a cylinder base. It's a circle. So we're going to find the area of a circle. 1/3 area of a circle times the height. Put all the numbers in there, calculate, and you should be able to get this volume here. Again, in yards cubed, because that is how many cubes, 3-dimensional cubes, would fit in there. Another problem. Find the volume of this football in terms of pi. Whenever it says in terms of pi, it means in your formula you're going to have pi, but instead of approximating pi with 3.14, just leave the pi in the answer. Do not multiply by decimal. Just leave pi in your answer. So try it here. Okay, we learned the volume of a sphere is given by this formula. We can put in our radius here. It's said in terms of pi, so again, we're going to leave this pi. And when you multiply everything else, you get 106 pi. We left the pi there. And I should have put inches cubed. I forgot the units, so inches cubed. All right, another problem. Try problem 4, finding the volume of each of these two solids here, the pyramid and the cone. And these ones, first one, the height is given, so you just use a straight volume formula, 1/3 base area times height. In the second one, like the one we just saw, there is no height given, but we do have slant height and this radius, so we can find the height first, and then we can put it into 1/3 base area times height to get this. Pretty straightforward. I hope you were able to get both those answers correct. Let's look at this last problem here. It says a cylindrical can holds 3 tennis balls. Each ball has a diameter of 6 centimeters, which is the same as the cylinder. Okay, so they fit perfectly inside there. And the cylinder is filled to the top. Calculate the volume of space in the cylinder not taken up by tennis balls. So how much space is there in that empty space inside the cylinder? All right, this can be a little bit of a multi-step problem, but you have all the numbers you need. That 6 centimeters is all you need. Go ahead and figure it out. I know you can do it. Okay, here's the approach. Volume of the cylinder, we can find the volume of the whole thing first. Okay, base area times height. So pi r. Notice the 6 centimeters was the diameter. It was across the whole circle. So the radius is 3. It's half of that. So we're using 3 here. Pi r squared. That's the area of the circle. Times 18. There's our whole volume. The radius of the sphere, so volume of one ball is calculated. 3 balls are here, and you do entire cylinder minus 3 balls.